Hello everyone, welcome to QST seminar. Today we are very happy to have Zohar Komargodski from Stony Brook. He'll be talking about giant vortices and the Ricci limit. Over to you, Zohar.
Very well, thank you so much again for the opportunity to speak. Please stop me at any point with questions or comments. I'll try to start a little bit slow for those who might be joining late. So I'll start with some little bit dumb motivation that's not really necessary for this group. But it's, of course, something that's been appreciated for the last several decades, that sometimes there are strongly interacting many body systems, and developing analytical tools to treat such systems is very important. It's considered an important problem in theoretical physics. And one concrete problem that received a huge amount of attention is the problem of understanding local operators in strongly interacting theories, the behaviors of local operators, their correlation functions, and in particular at fixed points of the renormalization group, at CFTs, conformal field theories. These local operators are characterized by a scaling dimension, spin, and this CIJK stand for 3-point functions. So sometimes people call the set of 3-point functions and the space of local operators the CFT data, because it's known that you can reconstruct, in principle, any correlation function if you have the full list of local operators and the full list of 3-point functions. So it's considered important. It's considered an interesting problem, and also makes contact with experiment to try to understand something analytically about the space of local operators and their correlation functions. A lot of the work on this subject is numerical, so it would be nice to have some analytical control. So one interesting numerical technique.
Zohar, can I already ask you a remedial question? I'm very sorry.
No, sure. Any question is fine.
Is this local data enough to also completely determine the correlation functions of the CFT on manifolds of non-trivial topology? I don't know the answer as well as I should. Sorry.
If you are asking about partition functions, then certainly this is not enough.
Okay.
I mean, there are certainly, so for instance, in condensed matter parlance, another interesting object that you can define in a conformal field theory are impurities. And in high energy physics, we would call them conformal line operators.
Okay.
So certainly it's not an obvious problem to reconstruct the conformal line operators from this data. And it's actually, I don't actually know if it's even possible.
Okay.
In addition, of course, there are topological issues that the space of local operators completely misses. So what I'm saying is that there are actual physical observables that this data does not include, such as conformal surfaces, conformal lines, and also there is topological data that this does not include. So certainly this is not exhaustive, but because experimentally it's most easily measurable, this received most of the attention in research.
Sure.
In fact, if you ask what is the space of line operators that are conformal, very little is known about it. And I've dedicated most of my time in the last year to that problem, but I'm not speaking about it today.
Okay.
So yeah, this is something that we know a lot about experimentally, as you'll see. There will be many graphs in this talk from experiment in Monte Carlo. A little bit less is known about conformal lines and surfaces. And about the topological aspects, even less is known, I believe. So condensed matter theorists developed a huge theory of the topological aspects of gapped vacua, of trivial. This is called SPT phase.
Right.
However, there isn't any sort of theory for the SPT phase or whatever you might call it for gapless phases.
Yeah, that's what I was getting at. I see. Okay. Okay, nice. Good to know. Thank
There's
you.
so gapped vacua are classified, the topological aspects of gapped vacua are classified by some sort of K theory. There's a nice cobordism, a classification by some cobordism cohomology groups.
Okay.
But if you ask what is the classification of the topological aspects of gapless vacua, there is no K theory or any known cohomology group that classifies that. So this is a wide open question that is very deep and interesting.
Okay. Okay. Thank you. Thank you so much.
A little bit is known about it, I can tell you later, but it's really off the main
Sure.
the point of this talk.
Sure. Sure. Thank you.
So, of course, this very famously 12 years, well, I guess, but yeah, 12 years ago or so, these people launched a numerical program that uses the associativity of the operator product to gain some numerical control over this data of local operators and operator product expansion coefficients. And this program was very successful, but it's numerical in nature. And today I don't want to talk about numerics. I want to talk about what do we actually know analytically about the space of local operators and their operator product expansions data. So I will concentrate today on heavy operators. And when I say
one question, it may be tangential, but what do you expect about the solution space to this equation, a single equation of this sort, where the OP coefficients are positive?
Single equation? This is like a matrix of all possible equations with arbitrary external states.
But let's say I consider one equation of this sort with identical operators. Do you expect the solution set to be discrete?
No, I think Dalimil Mazach 2 years ago invented the very clever unpublished argument that shows that you should not be able to shrink the space of solutions to a point. The islands would not completely shrink to a point.
But in the Ising model, in the Ising model thing, people, so how is one able to narrow down to the Ising model?
In the Ising model, if you look at the literature, the islands have shrunk to something like 10 to the minus 5.
Oh, I see. So
Dalimil devised an argument which is not a proof, which is why he didn't publish it. But he devised an argument that it will actually never shrink to a point.
Interesting. Okay, thank you.
Or one correlator. You need more correlators to shrink it to a point, hopefully. But of course, most people expect that the space of solutions is discrete. But you have to include arbitrary external states, not just one external state.
Yes, thank you.
So I will talk about heavy operators today. I do not believe there is much to say from analytics about light operators. There are like heavy operators are analogous to high energy states in quantum mechanics. And about those, you might be able to say something using ergodicity, chaos, semi-classics, but you don't really expect to be able to say something concrete about the low-lying states. So today I'll be using the operator state correspondence, which says that local operators with scaling dimension delta map to energy eigenstates on an auxiliary sphere. And for heavy operators, those would be high energy eigenstates on the auxiliary sphere. And then we will use intuition from condensed matter physics and even some experiments to try to guess what could be those high energy states on this auxiliary sphere. I won't say the word auxiliary every time, so I'll just assume that this map is familiar to everybody, and we can use the eigenstates on this auxiliary sphere to learn about the scaling dimensions in flat space for local operators. So the concrete question that I'll discuss today would not be about generic heavy operators, because there isn't much to say about those. You could say that they are black holes or something, perhaps. I'll talk about a more concrete question that is more easily accessible to experiment, which is, what can we say about the lightest operator with some given charge and some given angular momentum? That is a concrete question that can be answered. So you just look at all the possible local operators carrying some charge Q or carrying some angular momentum J, and you ask, what is the lowest lying operator? That's a question you can ask. Here are some references to people that considered this question and also the variant that I won't discuss today. And let me just jump in. So let's first review what is actually known about the lightest operators of some given spin J. Again, as I said, it would be useful to use this mapping to an auxiliary sphere. And there is a very nice picture that emerges if you study this question. So it turns out that the answer is completely universal and it's independent of the model. And so the answer is the following. If you look at the operator product expansion of any local operator with itself, you will find eventually in the operator product expansion some operators that, loosely speaking, you can think about them as phi and j derivatives inserted in some particular way. And it turns out that the scaling dimension of these operators for a very large j is barely renormalized. It's almost not renormalized. So the scaling dimension of the corresponding state, or the energy of the corresponding state, looks like two particles that only have tiny interactions. And so on the sphere, on the auxiliary sphere, you can think about the state as two particles that are spinning around the equator of the sphere at very large angular velocity. And the scaling dimension is just j from the j derivatives to delta phi from the two phi partons. Sometimes I'll call those phi partons because they look like particles in this picture of the state on the sphere. And then there is a tiny correction that is actually completely known from tiny interactions between those spinning partons. So every strongly interacting CFT, if you go to the large angular momentum domain, we actually know the ground states. Those states are the lowest possible energy states, and they have only tiny corrections compared to free field theory. So sometimes people say that there is asymptotic freedom at small angles because small angles is conjugate to large angular momentum. So it's analogous to asymptotic freedom at high energies in QCD or small distances. Here we don't have here we have a fixed point, but we have asymptotic freedom at small angles or large angular momentum, because every theory would contain basically a free sector corresponding to these two particle states. So let me show you that this is indeed seen in an experiment in Monte Carlo.
Sorry, just before you go there, Zohar, the tau min value of the exponent is also something that you can obtain just analytically?
Yes, actually, yeah, I was a little bit too vague in this formula. I should have fixed it. Tau min is 1 in all the theories we'll talk about today. It's exactly 1. And also this prefactor is known exactly as I mentioned here. I just didn't reproduce this prefactor. It contains a bunch of gamma functions. It's analytically known.
Okay. And sorry, just one more question. For at least large central charge, etc., if you could have a ADS dual, do these exponents just follow from locality in the bulk? Because you have these two spinning particles, maybe they are large enough distance effectively for very small angle scattering or something, and then just bulk locality fixes it, or is that not true?
Okay, yeah, I have two comments to make about it. First of all, this saying that this is the true ground state at large angular momentum is a little bit in tension perhaps with the common wisdom, which is that the ground state at large angular momentum is a black hole. Okay, so you might be worried about it, but the resolution of this paradox is simply that the black hole answer is incorrect. The true ground state at asymptotically large angular momentum is not a black hole. It's these two particle states. That's comment number 1. The black holes could be the ground state at angular momentum, which is of order n squared. But when the angular momentum is the largest parameter in the problem, the black holes are not the right answer. And to your question of whether you can obtain this result from ADS, the answer is yes. This was done in this paper in 2012.
Okay.
They have argued that you can also understand this result in ADS because the dual state to these two rotating particles in ADS is just two particles rotating very far from the center of ADS around each other.
Okay.
And the forces that they exchange are gravitational forces, which kind of die off at large distances.
Yeah, that's what I was thinking. Okay, thank you so much.
Yeah, so the ground state is not a black hole. This is the true ground state at large angular momentum.
I see. Thank you.
I mean, this might be actually the ground state even when J is of order n squared, because as you know, there are no black holes there are no extremal black holes.
Mhm.
This is like the zero temperature ground state
Mhm.
at large angular momentum. And now we know from the work on JT gravity that there aren't any extremal black holes anyway. So this might be the right answer even in n equals 4 when j is not even the largest parameter, but when j is only of order n squared. I don't think this is the right answer when j is of order n squared, only when j is very large. But it could be part of the answer even when j is of order n squared.
Okay.
In particular, I don't think this is the right answer when j is of order n squared because we also have a huge theory of the fluctuations around that ground state, and it doesn't match what you might expect from JT gravity. Okay, so anyway, this is the true ground state, and it's not a speculation. It was proven using the conformal. It's a consequence of the conformal bootstrap equations in some light cone limit. So it's a completely universal conclusion that's model independent. Here you can see the experimental verification in the O2 model. Here they denoted the spin by L rather than J, and tau is what's called the twist. It's delta minus J. So you just move J to the left-hand side, and you should see a function that's approaching a constant in a convex fashion, concave fashion, and that's what you see for various. So sometimes people call these things Regge trajectories. You choose two partons, you start spinning them, and you approach this asymptotic constant. And how you approach this asymptotic constant is slightly sensitive to which partons you choose. So these three channels correspond to three choices of the partons that you can do in the O2 Wilson-Fisher theory. Okay, so this seems, so the yellow, the blue and the red lines are theory, and the dots are the experiment. And you see that the theory matches the experiment even for very small angular momentum. You might have, as I said, this is proven rigorously only for large angular momentum. But even for angular momentum like 5, 4, 3, the theory and the experiment are basically on top of each other. So it's very impressive. I don't know why it works so well. Probably nobody does.
I have a question.
Yes.
So when you say that phi delta J, phi is the ground state, what exactly do you mean? You mean the phi delta J, phi acting on the vacuum or something?
No, I'm just saying you can ask what is the lowest lying operator with a given spin. Or you can ask the corresponding question on the auxiliary sphere. What is the lowest lying energy eigenstate with some given angular momentum?
Okay.
So this is the answer.
And what is J in that case? I mean,
J is the angular momentum.
Yeah. So for different J, you would have different, I mean, states, right? So if you are saying
Yes.
that it's ground state, you have to specify J in some sense, is it not?
Yeah, J is fixed. This operator, which corresponds to a state, is the ground state for a fixed J. And that's true for every J.
I see.
Sorry, maybe I misunderstood the question.
No, I was just saying that, I mean, you have to, I thought that you were saying that there was a unique ground state and then you build on top of that ground state with other operators. But you're saying that for every J, there is a specific ground state, which is given by phi delta J phi.
Right, it's a microcanonical question. You have a microcanonical system on a sphere, and you ask what's the lowest lying energy eigenstate for some fixed J.
I see.
So this is the answer for a fixed J.
I see. Okay.
You cannot, yeah. Sectors of different J do not communicate since they have different global symmetry quantum numbers.
So Zohar, the states at large J, does this mean that they form a Fock space?
Yeah, that's the asymptotic freedom that I mentioned. At small angles, there is an emergent Fock space.
And then the generators of this Fock space, I mean, has there any, I mean, is there something that one can say about those asymptotic values?
Values of what?
Of energies, of the twists.
Oh. Well, this is the
there
formula.
are certain generators that generate the Fock space, right? So I was wondering if one can say something about those generators.
I'll talk about this I'll talk about this Fock space today, but for the case of many partons, maybe some things will be more. Okay. I mean, today I'll talk, this is just a review. Today I'll talk about a slightly different question where there will be many partons, not just two.
Yeah. Okay.
But yes, there is a Fock space. You can add derivatives in various ways that do not change the angular momentum. For instance, you can add two derivatives with contracted indices. So you can think about it as an excitation in the Fock space, and it has nearly free field scaling dimensions with small corrections that you can compute exactly. People call it daughter trajectories. So these are the main trajectories, and those Fock space excitations are daughter trajectories.
Okay. Thank you.
Yeah, so there is a Fock space indeed.
And why exactly don't the phi delta j, phi for different j communicate with each other? Because I could presume that there would be scattering between those states, which.
Well, by communicating, I meant that the Hamiltonian is block diagonal, because once you fix J, your Hamiltonian commutes with J. So once you fix some quantum number, you cannot have off-diagonal terms in the Hamiltonian.
Right.
It's like a global charge. So your Hamiltonian is block diagonal in the charge.
Okay.
J is just the eigenvalue of the rotation of this auxiliary sphere.
Right.
So you cannot fix it and ask about the properties of the system within that state, within that subsector.
Yeah.
Of course, there's 2-to-2 scattering, but at the level of the Hamiltonian, it's block diagonal.
Correct.
Okay. Here I mentioned that in the O2 model, tau mean is 1, as I mentioned before. So today I want to talk about a question that emerged much more recently, and it's extremely interesting. At least I found it conceptually interesting. I'll show you why. People have asked what happens when you fix Q, which is a U1 charge, and you want to look at states with very large angular momentum. Okay, so here I only talked about such states, and they could have maybe Q equals 1, Q equals 2, but let's suppose we fix Q. Let's say Q equals 100. It's a U1 charge of a local operator. And now we ask, what is the ground state at very large angular momentum? So the main observation that one must make about this problem is that now we have Q partons, because we have to have charge Q. So the picture is that we have Q partons circling around the equator. And now there are many, many ways to spread around the derivatives, because you only have to maintain that the total number of derivatives would be J. And because of this asymptotic freedom at small angles, there is very little dependence on how you actually spread the derivatives to leading order. So the energy of any state, as long as the sum of the derivatives is J, is going to be J plus Q, the Q partons. This is just the rest mass of the Q partons, and then tiny corrections that go like the charge cubed over the angular momentum J. And this system now has a huge entropy. There is a huge approximate degeneracy to leading order. So once you neglect these corrections, it's exact. It corresponds to just changing the relative distance between these partons in the ADS picture, or even on the sphere. You can think about it as changing the relative distance. And it leads to a huge entropy that goes like exponential of the charge Q. Okay, so once you have non-zero Q, or let's say Q bigger than 2, the problem becomes interesting, because there is a huge degeneracy that should be lifted by some huge degeneracy within every Q and J that should be lifted by some small corrections that actually were never computed. So this is an open problem to compute those corrections. We just know that they scale like Q cubed over J and that they're negative. But we don't know exactly the expression, so we don't actually know at the moment how this huge approximate degeneracy is lifted. So why is this interesting?
Sorry, Zohar, may I ask one question here? So this result of Q cube over J, it just assumes Q large and J large, I gather, but is anything assumed about the ratio? Or
right, so you can see, this is the next slide.
Oh, sorry.
Yeah, this whole formula is rigorous when J is the largest parameter, because then we have this asymptotic freedom. We have this tool from asymptotic freedom.
Yeah.
Small angles. But you see that when J becomes smaller than Q squared, something fishy is going on, because these small corrections begin competing with this when J is of order Q squared. And so this picture breaks down.
Okay, I see.
So we see that when we have finite charge, the picture breaks down when the angular momentum is of order q squared.
Mm.
And also this formula becomes like an exponential of the square root of angular momentum.
Mm.
It's actually very reminiscent of the entropy of charged spinning black holes, non-supersymmetric charged spinning black holes. Anyway, so there's this situation that even in this limit of large J, you see a huge degeneracy.
Mm.
And for angular momentum of order q squared, the whole thing breaks down. The large spin expansion breaks down because we see large interactions between the Spartans.
Mm.
Now,
one question,
yes?
sir, just before you move on. This degeneracy is basically how you distribute the derivatives in the middle?
That's precisely correct.
Okay.
And nobody has computed yet exactly what is the dependence on the number of derivatives on each partons. So Tolydic order, it doesn't matter, but there is some function that must be computed. It's a bootstrap question of a sort that needs to be solved. We believe, of course, that the lightest operator is when all the derivatives are like the same. So all the distances are equidistant. But that hasn't been shown. And basically the belief is that once this becomes large, then there is an instability in the partons to clamp together and to condense.
I see.
And it's kind of important that this sign is negative probably, or at least sufficient not too positive, because that means that the partons interact by attraction. So they kind of want to attract. So the picture is that when J is of order q squared, there is some attractive interaction. You can actually compute the interaction analytically in the O2 model. So the interaction between the partons comes from a repulsive electric force. Think about it in the ADS picture. It's much easier. It's just a bunch of particles rotating around the center. And each of them has charge 1 under Coulomb interactions. And of course, gravitationally, they all attract. So you have a bunch of particles spinning at long distances in ADS, and they experience attraction from gravity and repulsion from electromagnetism. And you have to balance the two forces. If you read papers on the weak gravity conjecture, you might think that gravity is going to lose. But that's actually not true. Exactly the opposite happens. In the O2 model, we computed it, and gravity wins. So it's attractive. So we see.
Sorry, just one more question.
Yes.
Sorry, one more question before you move to this. I mean, you could have asked this question in the Ising model, right? Some theory without U1 symmetry, because this parton picture presumably is still valid at large.
Yeah, but there is no repulsion because there is no electromagnetism. So the question becomes a little bit moot. It's obviously going to attract.
I see.
Right?
I have a naive question. Like, why don't these operators develop masses in quantum corrected, when they're quantum corrected by loop effects? Why don't they develop masses?
Well, it's an excellent question, but I'm not planning to give you a full explanation now. I can do it after the talk.
Okay,
The point is that in any conformal field theory, even a strongly interacting one, in the sector of large angular momentum, the coupling goes to 0 magically. So all the loop corrections are suppressed at large angular momentum. You can see it in the epsilon expansion if you're a fan of that story. You can take the angular momentum to be very large, and you'll see that all the loop corrections go to 0 as a power of J. Hence this formula.
Okay.
So there is attractive interaction between these partons, and you can then guess that maybe when J is very large and Q is very large, but J is smaller than Q squared, then this picture of the partons is not true anymore. And maybe there is some new state with a condensate because there is an attractive interaction. So you might generate a condensate. But it's very difficult to guess what it's going to be. So instead of guessing what it's going to be, I'm going to now give you a review of the other regime, and then we'll build a coherent picture. Now we're going to forget about angular momentum and just ask what happens to a conformal field theory like the O2 model when the charge is very large, but the angular momentum is going to be not a big issue anymore. So we're going to assume that we have large charge. So the charge density on this auxiliary sphere is the charge divided by the volume of the sphere, which defines a high energy scale, mu squared. In a condensed matter language, it's a high energy scale. It's much bigger than the scale of the inverse radius of the sphere. So you can try to ask what is the effective field theory at large charge. So we had an effective field theory at large angular momentum. This was the spinning partons. Now we are looking for an effective field theory at large charge. So unlike the large angular momentum limit, there is no unique answer at large charge. One has to guess and then confront the guess with Monte Carlo or experiments. For the O2 model, we now have very convincing evidence that I'll quote soon, that the answer is that it's a superfluid. So the effective field theory of the low-lying modes between the scale 1/r and the scale mu is a superfluid theory, a conformal superfluid theory. And that gives us a very good understanding of the scaling dimensions of operators with large charge but small or zero angular momentum. Again, you might have thought that the answer is a charged black hole, and that is not true. The answer is not a charged black hole, it's a superfluid, which is something like a, in ADS, you might call it a boson star. That's the true answer at large Q. So what is this conformal superfluid? It's basically a theory of a pion, a single superfluid mode, which realizes the conformal symmetry non-linearly. So the ground state is some charge Q state, which loosely speaking corresponds to Q partons on top of each other with no angular momentum. So this is the action that was first written down 7 years ago. It's just an action that realizes non-linearly the conformal symmetry on the superfluid mode. So there is a bunch of Wilson coefficients, and Wilson coefficients give you an answer for what is the scaling dimension of the smallest operator of charge Q in the O2 model. And the thing you need to remember is that it's going to be Q to the power 3/2. So the scaling dimension goes like the charge to the power 3/2. That's also the correct formula for a black hole. For a charged black hole, the scaling dimension goes like Q to the 3/2 in 2+1 dimensions. But a charged black hole has entropy, and a superfluid doesn't. So this is not a black hole. This is just effective field theory of a single superfluid mode. Okay, so people use this effective field theory to make predictions.
Sorry, so
And
this is to say that when it's of order n squared, then there is a degeneracy, and when it is very much higher than that, there isn't. Is that the?
I don't even know that when Q is of order n squared that there is a degeneracy. Even that might be wrong, because we now know that there is no degeneracy for extremal black holes. Like if you literally take the zero temperature limit, there isn't even one state.
Okay.
You know what I'm talking about? That there is this correction by Ashok-Sen to the entropy, which has a logarithm of the temperature. You know what I'm talking about?
No, not quite. No.
So people computed the density of states of the extremal black hole. And people in the past thought that the answer is that there is a lot of states due to the entropy. But the entropy receives logarithmic corrections that Ashok-Sen computed. And one of the logarithmic corrections is a logarithm of the temperature. And when you send the temperature to 0, the whole thing, the entropy goes to 0.
Okay, I see. Thank you.
So there aren't any states actually at 0 temperature.
Yeah.
So you could say that there is no such thing as extremal black hole. There is no such thing.
I mean, in JT gravity without supersymmetry, for example, again, the degeneracy goes to 0.
Yeah. So I don't actually know if any system has degeneracy. I don't believe there is. If you think about it from the physics point of view, having a degeneracy with no symmetry is insane. So I believe that this answer is actually the correct answer for large charge, even in n equals 4.
But if you say that there are no degeneracies, how would you explain entropy of a black hole in the ground state?
But there is no entropy. Ashok-Sen found that it's 0.
I mean, I think he found that the correction is logarithmic, but the area law has to be correct, right?
No, for extremal black holes, the logarithm wipes out the leading term completely.
Yeah. At sufficiently low temperatures.
So the area goes to 0 or something?
No, the area remains finite, but the full entropy is an exponential of the area multiplied by the temperature. So there is a prefactor, which is the temperature. And when you put the temperature to 0, the exponential of the entropy doesn't matter anymore because the prefactor goes to 0.
Yeah. Yeah.
I mean, in the Turiachi Iliescu paper, they compute such things, and do they come to the same conclusion that the
Yeah.
degeneracy is completely zero, and
Yes.
there's an S2 part which gives rise to
No, the Turiachi Iliescu paper comes exactly to the conclusion that I just said.
Yeah. Even, I mean, with all due respect, even before that paper, for the non-SUSY extremal black hole, just the result of JT gravity holds and shows that it goes to 0, as Zohar was saying. It's sine hyperbolic square root of E goes to 0, like that. Okay, anyway.
That is the ADS2 part of the calculation, but there's still an S2 part which gives rise.
It's an exact calculation. JT gravity is an exact approximation at low enough energies for a black hole, even with
but think about it also, forget about the details, think about it as a physicist. You can't expect exact degeneracy in a non-supersymmetric system.
That's true.
And this answer of the superfluid makes much more sense.
Zohar, sorry, one remedial question, very remedial. How are you preserving translational invariance with 3 derivatives?
What? This one. No, okay. This action looks bizarre.
Yes.
It's very non-local. But the point is that we don't study it for this variable. We expand around the background that non-linearly realizes the symmetries. And we actually expand in the fluctuations. And the action for the fluctuations makes sense.
Okay. Thank you.
We actually do the same in pion physics. But yes. Okay. So the fluctuations. Okay. This is the story for just large charge. Everybody. And also it was completely proved. It was almost proven by now on the lattice that this is the right answer in the O2 model. I don't know if it's the right answer in n = 4, but in the O2 model, this is certainly the right answer. It's now incontrovertible. It has incontrovertible evidence on the lattice. So you can now try to add a little bit angular momentum, right? Because I want to plot the phase diagram as a function of J and Q. And adding a little bit of angular momentum is completely trivial because these fluctuations of the phonon, the so-called small fluctuations of the superfluid, are called phonons. They just have a quadratic action that you obtain by expanding this cubic action. And they have some dispersion relation on the sphere. And they move at the speed of sound, which is 1/√2 of the speed of light. And they lead to a Fock space. And this Fock space allows you to add a little bit of angular momentum to the superfluid. Not much, just a little bit. Why am I saying not much? Because, of course, you cannot excite a lot of phonons. Then you'll exit the regime of effective field theory. So this is the formula that you get for very small angular momentum, which is at most square root of Q. You can just have a superfluid and add a few phonons. And since my main goal is to plot the full phase diagram, I want to know how to go beyond adding a few phonons to the superfluid. And for that, we have a lot of intuition from experiments in superfluids. It's known that in superfluids at the beginning, there are a few phonons. But when you start spinning the superfluid more and more and more, vortices appear. And it's a very nice problem in mathematical physics to understand these phase transitions between no vortices to one vortex. And then you get a lattice, a very nice lattice of vortices that is called Abrikosov lattice. So it's also described in Feynman's lectures on statistical physics, how to find this Abrikosov lattice of vortices. So it's basically known from experiment that you can add even more angular momentum to a superfluid by adding vortices. Okay, so let me just explain physically why vortices are a useful way to add angular momentum. There is a very simple explanation. So the dynamics to leading order in the non-relativistic approximation, vortices in a superfluid behave like electrically charged particles behave in a magnetic field. So everything you learned about the Lorentz force acting on charged particles holds for vortices. That's actually why vortices spin around the sphere. like in a drift motion that's familiar from plasma. So we have some magnetic field. We have some kind of auxiliary magnetic field on this sphere. And so when you put an electric charge in a magnetic field, we have the effect of Dirac, that there is an angular momentum that you obtain by multiplying the vortex times the magnetic field. So basically vortices appear when you start spinning a superfluid because of this phenomenon that the electric field combines with the magnetic field to give you a very large angular momentum. So that's why for the system, it's very beneficial to create vortices because they carry a huge angular momentum. So indeed, we basically have this, it's known that in the O2 model, you start spinning the superfluid a little bit, you'll just create vortices like you do in a real superfluid. And that can take you so far. At the end, you create this lattice of vortices, which is very nice. And that takes you all the way to angular momenta of order q to the power 3/2. What happens at angular momentum of order q to the 3/2 is that the rotation speed of this, the vortices spin around the sphere. And at some point, the rotation speed exceeds the supersonic limit. So they start spinning supersonically, and then presumably there is some superradiant instability. It hasn't been proven yet, but people are working on it. I'm also thinking how to prove that. So there is some supersonic instability, and then this picture becomes useless. So that's...
Zohar, can I ask you one, very elementary question that's confusing me? The energy of a vortex is not just something which comes out from the pion physics, right? Because the core is stabilized by the restored phase and so on. So I might be getting confused, but when you're computing delta here, what is it? Does it include the energy of the vortices?
It's an excellent question. Somehow you spot all the things that
No.
So the point is the following. The energy that comes from the core of the vortex is not determined by effective field theory. It's a new Wilson coefficient that is not included. None of those Wilson coefficients would allow you to fix the energy of a single vortex.
Yeah.
It's a new Wilson coefficient. You can call it C.
Okay.
Now, what's the point? In some models, it could be that it's infinite. There could be models where to create even one vortex, you need to pay infinite energy. Those models would have what we now call a one-form symmetry, because one-form symmetry is something that protects against the... But with the O2 model or n equals 4 superangles don't have any such symmetries. Mm-hmm. And so it's widely believed that vortices have a finite Wilson coefficient. So even without knowing this Wilson coefficient, you can predict the scaling energy of the ground state. And this happens for the following magic reason. So this new Wilson coefficient doesn't enter the formula for the scaling dimension. Only one coefficient enters, which is the same coefficient that appears in the action here. So why does this new Wilson coefficient not appear? This new Wilson coefficient doesn't appear because once you create vortices, they also experience logarithmic repulsion. And that parametrically overcomes the unknown Wilson coefficient. So I only displayed two terms in the formula for the scaling dimension in the phase with vortices. But if I wanted to display more phases in the more terms in the expansion in J over Q, I would eventually encounter this new Wilson coefficient.
I see.
But because I only kept the two leading terms in this domain between square root of Q and Q, or here between Q and Q to the 3/2, I kept only the two leading terms. So this Wilson coefficient doesn't come in.
Okay, thank you so much.
I have another naive question. Like, do the vortices have finite energy?
Well, yeah, that's what we just discussed. It's widely believed that in the O2 model they do. And their energy is given by the only scale in the problem, which is what I define here, mu. So it's because O2 doesn't have an intrinsic scale. Therefore, the radius of the vortex and the rest mass of the vortex have to be given by by inverse mu and mu, respectively. There is no other scale.
So in that case, doesn't the ground state also acquire a mass gap or something?
Well, that's what I said. It is true, it contributes, but these two terms are more important, or these two terms are more important. So there is a correction, but that correction is suppressed by a larger power of J over Q to the 3/2. which comes from the effect that you mentioned. So there is one more term that is much smaller than those two, which would be sensitive to this contribution that you mentioned.
No, I'm not talking about the scaling dimension. I'm talking about whether the ground state acquires a mass, because if it does, then it's no longer a conformal field here.
Oh, no. The mass of the ground state or the energy of the ground state is delta. That's the point. The scaling dimension by radial quantization is the same as the energy of the ground state. And once this ground state acquires a mass, it doesn't violate conformal symmetry. No, it's just a small correction to this formula.
Okay.
I hope it makes sense. Actually, all these details are in the paper with Gabriel Cuomo, who is my co-author on this paper.
Okay.
So you can find the fully explicit discussion that would be way more than you want to see about these small corrections, including this Wilson coefficient.
So Zohar, sorry, one question, just to see whether I understand. So far the discussion was in general dimension before the vortices. Vortices were introduced, right? Now this is specific to 2+1 dimensions?
This is specific.
Okay.
To this whole thing, you see, because of this.
Yeah.
This is specific. Yeah. This is how the superfluid is realized in 2+1. If you want to ask me what happens in 3+1, it's not known.
Okay. Yes. Thank you.
Only 2+1. We only consider 2+1.
Yeah.
Okay. So we have. I think maybe I convinced you that we have a good prediction for the ground state on the sphere or the scaling dimensions for J bigger than Q squared. When J is bigger than Q squared, just to remind, we have registry and partons and a Fock space of partons. And when J is smaller than Q to the power 3/2, we have this superfluid with vortices. And this makes a lot of predictions for the scaling dimensions in the O2 model and many, many other field theories in 2+1 dimensions, probably all the field theories in 2+1 dimensions with global symmetry. And well, some of it was already checked in Monte Carlo, some not. But this is what we claim. Now, we have a missing gap. We have a gap between Q to the 3/2 and Q squared. What is going on between Q to the 3/2 and Q squared? So I already gave you a hint. We have two hints by now. One hint is that we have these partons in the registry that wanted to condense. Another hint is that the vortices, those spinning vortices, they become supersonic at the lower end of this domain. So when something becomes supersonic, we have this kind of cone. So they also seem to want to be. So basically, these two things lead to a guess, which is that there is a giant vortex between Q to the 3/2 and Q squared. What is a giant vortex? It's a new solution to the equations of motion of a superfluid. It's a very explicit solution, but it has some weird features, which is that this is actually a picture from an experiment where a giant vortex was seen. It's a situation where the superfluid is spinning very fast, much faster than the speed of sound. But the price that you pay is that there is a gap here. So there is no superfluid inside and no superfluid outside. And it was seen in an experiment 2 years ago. So we decided to look for such a phase also in the O2 model, and we found a solution on the sphere, on this auxiliary sphere, where there is a gap here, so no superfluid, and then a superfluid in this layer in between, and a gap here. And it's a very explicit solution. You can compute the charge, the angular momentum, and you can quantize it. So now I'll just spend 5 minutes to tell you the surprising things we found when quantizing this solution. We believe it's also relevant for real-life vortices, because these people just found this giant vortex, but people haven't studied the fluctuations yet. So let me just tell you some features of this. So first of all, there is this domain of the superfluid. If this domain is too small, then effective field theory breaks down. And this happens when J is of order Q squared. So this giant vortex beautifully matches what was missing before. Let me just go to show it here. We had this story with the superfluid with the vortices and registry, and the giant vortex magically sits in between. We get both sides of the inequality for the allowed region of the angular momentum from requiring that the middle region is not too small, and from requiring that the boundary layer is not too large. So these two requirements fix the two sides of the inequality, And this seems to be the right phase between q to the 3/2 and q squared. So this is the conclusion. But now in just 5 minutes, I want to tell you about the fluctuations, quantizing the fluctuations around this new solution, because that's where the interesting stuff is. So first of all, you can compute,
Zohar, sorry to slow you down, but just in terms of a picture, is it that the usual vortex has just one point in the center where the phase is strictly the normal phase, in that the wave goes to 0, and here in the giant vortex that region has grown to some finite size? Is that right?
100%. 100%.
Okay. Thank you.
It's called the giant vortex because somehow the core grows to a macroscopic size. People have seen it in experiment, but I think we found the solution for the first time. We found the full solution in the superfluid equations of motion with these features.
I see.
One interesting theoretical aspect here is this boundary layer between the normal phase and the empty region. One has to impose boundary conditions, and it's very subtle. This is an interesting problem in effective field theory to understand these boundary conditions. I wrote some comments about it here, but I'm not going to explain them. I'm running out of time because the physics at this boundary condition is non-standard. So, but anyway, it's a problem. So you can compute the scaling dimension corresponding to the giant vortex, and lo and behold, you find exactly like in Regge theory, something linear in J. So that made us very excited. We showed that it's so two things show you that you're on the right track. First, the giant vortex lives exactly between q to the 3/2 and q squared from effective field theory considerations. And secondly, the energy is exactly linear in J. So it makes very nice contact with Regge theory. These are two small comments. And most interesting is the fluctuations, the Fock space. Remember that in the Regge theory, I told you that there is an infinite Fock space due to the fact that you can rearrange the derivatives without paying any price. So when we quantize the fluctuations of the giant vortex, amazingly enough, we found the exact same thing. So we found the chiral theory, which is a little bit like the compact boson in 2D, but the compact boson has a ground state and no infinite degeneracy. But we have something like a compact boson where you can turn on both negative and positive M modes. So there are creation operators with negative frequency. And so there is infinite degeneracy in the Fock space. And there are also daughter Regge trajectories that I mentioned to Abhijit before. So the spectrum of fluctuations of the giant vortex is a chiral theory with infinite degeneracy, exactly the same as in Regge theory, exactly the same Fock space. It's really one-to-one. So the giant vortex seems to be a close friend of the Regge regime, except that it doesn't have partons, but it has this nice, smooth, normal superfluid phase. So this is the action of fluctuations around the giant vortex. It's a bizarre quadratic theory that I haven't seen before, but when you quantize it, you discover that it has creation operators with negative frequency and an infinite degeneracy. So it describes chiral modes, but the chiral modes are bizarre. They're a little different from the chiral modes that you encounter in normal 2D systems. So the reason that this is allowed to spin supersonically is because now the chiral modes move at the speed of light. So the limitation from the supersonic speed is no longer an issue. That's why the giant vortex can spin very, very fast, supersonically, in fact. Okay, so the giant vortex.
Sorry, Zohar, just repeat that last comment again, please. Just one, sorry. About the
Which one?
No, the supersonic, why they can.
Okay.
Just the
so
last
if you read the classic literature on vortices, for instance, Feynman's lecture on this phase of the many small vortices spread on the sphere or on the trap, people knew that if you kept spinning the trap faster and faster, eventually this wouldn't be a stable phase. Because at some point, the vortices will start moving faster than the speed of sound, which is 1/√2 of the speed of light. And this put a bound on for which angular momentum this could be the ground state. The bound was q to the 3/2. So here I'm quoting it in the language of the O2 model, but if you look at the literature on traps or Landau or Feynman, whatever, you'll find the same physics in different notation. It's just the supersonic limit. So for many years, it was an open problem of what is the next phase of a superfluid. when we get to angular momentum, which would make the vortices go supersonically. And only 2 years ago, it was found experimentally that you get this thing.
Yeah.
And why is this allowed? They didn't explain it. They just observed that this phase is allowed to exist supersonically. But we found the answer, which is that actually the fluctuations are chiral modes moving at the speed of light. So there is no limitation from supersonic anymore.
Okay.
The fluctuations are not moving at the speed of sound. They're moving at the speed of light.
Okay. I see. Okay, thank you. I understand.
That's why this is allowed to go as fast as you want. The only thing that happens to this thing when you keep spinning it faster is that it shrinks. It becomes more and more narrow. And at some point, it becomes so narrow that you cannot really say that there is superfluid. And that's why there is an upper bound of Q squared. Where does this Q squared comes from? It comes from the fact that this could be so narrow that it wouldn't make sense to say that there is a superfluid. This Q squared was not reached experimentally yet. But what I'm telling you should give you a prediction of what happens when they reach this angular momentum of order Q squared. And what should happen is that you'll get the partons of Regge theory, because we saw that that's the next phase. Basically, the superfluid would climb into partons that would spin around the equator.
Got it. Thank you.
Anyway, so the giant vortex has this very strange theory of fluctuations with infinite degeneracy, with very small splittings. To understand the splitting of this infinite degeneracy, you have to quantize the boundary layer theory. So it's a very important problem to understand the boundary layer. And actually, it's important for experiment because we believe the same infinite degeneracy exists in the experimental setup of the giant vortex. And this makes the whole picture, I think, very nice. Like all the phases glue very nicely. And the giant vortex displays a lot of the properties of the Regge theory. So it looks very promising. So of course, like Abhijit mentioned, it would be nice to do 4 dimensions. It's not known what is the analog in 4 dimensions. Nobody really showed yet that when the abrikosov lattice is supersonic, that it becomes the giant vortex. It wasn't shown in equations. It was only seen experimentally.
Sorry, Zohar, just one question. So this Hellerman and collaborators, this superfluid picture, is it valid in general dimension? Just not the vortices, but just the superfluid picture.
Probably yes. Even in QCD, it's correct. You know, QCD at large baryon charge is a superfluid.
Yeah.
Yeah.
So
yeah.
There, I mean, in this particular phase that is adjacent to the Regge theory, would that not at least? I mean, it may not be able to go any further on that vertical side, but the lattice side, but the lattice of vortices side, but maybe the one adjacent to the Regge trajectories.
You mean this one?
Yeah, the giant vortex. Yeah.
But you see, you have to find a solution.
Yeah.
We didn't find a solution in 3+1, only in 2+1.
I see.
It could be very easy. I just haven't tried, you know?
I see.
It could be very easy to find a solution in 3+1 where we just haven't tried.
Okay. Thank you.
Okay. So yeah, it would be nice to understand the order of these various transitions. We talked about many phases. We talked about Regge theory. I told you that the Regge partons condense, they become the giant vortex. The giant vortex expands, becomes the abrikosov lattice. But what is the order of all these transitions? Is it second order, infinite order, first order? It's not known. Also, yeah, I mean, it would be nice to understand how these Regge partons collapse. It's basically the process of collapse in ADS. You begin from particles that are spinning in ADS, and then you slightly lower the radius at which they spin as measured from the center of ADS. And at some point, the gravitational attraction becomes so strong that they collapse to a giant vortex. But it would be nice to write equations in ADS that demonstrate it. And of course, well, there are these other questions that I mentioned in passing to understand the boundary condition better and understand that how the boundary conditions lift the infinite degeneracy of the chiral fluctuations of the giant vortex. And then to understand this entropy. We see that these systems have a huge entropy because they all have infinite degeneracy to leading order. So it would be nice to understand the fate of this entropy and what is the gap actually at the end. Thank you very much for all the questions and attention. Yeah, I see a question from some data.
Yeah, so I was just wondering, I mean, if you, you're dealing with scalar degrees of freedom. What happens if you, I mean, for instance, the basic degrees of freedom in the problem are the fermionic degrees of freedom, right? The electrons and so on and so forth. So what happens if you start out directly with the fermionic degrees of freedom and consider operators of high angular momentum or high spin by considering operators of the form psi bar, gamma nu, etc., psi, and then consider the ADS dual of this theory by computing the correlation functions of the psi bar, gamma nu, etc., psi, and figuring out the corresponding scalar theory in the ADS which corresponds to this, and then via a HKLL type of protocol map to the 4D theory back. I mean, is that does that sort of make sense in some way?
Yeah, I think you can repeat this whole story for fermionic theories. So I just want to say maybe two small comments. I believe the large spin aspect is exactly the same. It's just the same. There are these operators that you mentioned with many derivatives, and they behave exactly in the same way. And in ADS, it matters very little whether these are spinning fermions or spinning bosons. They're spinning very far from each other. You can ask if there is, you can ask how come if you have a theory of fermions, how come you will get a superfluid at large charge? Like you may question this result that a generic theory with fermions at large charge would, be described by a superfluid mode. But I think it's actually correct. Somehow the fermions form a Cooper pair.
Yeah.
And they do lead to a superfluid at low temperatures at large charge density.
Yeah, the effective degrees of freedom are bosonic. I mean, the Cooper pairs give rise to bosonic.
Yeah, so like if you took some interacting fermionic theory in 2+1, I talked about the O2, but I think it's correct basically for many examples. If you took like supersymmetric Ising in 2+1 or some Gross-Navet model, I think these things that I said today would actually be correct, completely correct.
Yeah.
I think it's even correct for theories with the Chern-Simons terms, like U1 level K plus boson is still correct.
Yeah, that's all I wanted to say, yeah.
Sorry, Zohar, what would happen if you go to a little bit larger, if you increase Q in the Ising model? I mean, not Q, but the phi's, a bunch of phi's in the Ising model. If you start considering operators with lots of phi's in the Ising model.
Well, they don't carry any well-defined quantum numbers, unfortunately.
Yeah, but can you? But the parton picture is still there, right? So can one
No,
use that?
no. The parton picture is only good when they have lots of derivatives sprinkled.
Yeah,
between
so
them.
you have that. Let's say you do have that in the Ising model.
Yes.
And then you start increasing a number of phi's also, so that you try to exit this partonic phase. You don't exactly, you don't have this charge that lets you have this nice picture. But,
yeah, then this is just a funny state that is not actually the ground state of anything. So it might have an exponentially small probability to decay to something. Like it's not really the ground state of anything. It could, in principle, decay to other states with only 2 phi's and lots of angular momentum.
I see.
Right? So there could be some exponentially small decay probability. It won't actually be a completely stable or completely exact eigenstate. From the effective field theory point of view, it would be an eigenstate, but in the full picture, it might have an exponentially small decay probability. It's like in effective field theory, you could have a minimum, but if you look at the full potential, there could be some way to go over the barrier to a yet lower minimum.
I see. One more question. So I didn't quite understand this physical picture of clumping from the Regge picture, where you have these partons spinning very fast, and then, as you said, the gravitational attraction wins over the repulsion, and then they clump together. But I would have thought the clumping would happen in a way, I mean, where these partons would get together, right? I don't see the band structure coming out, where it's kind of, they fuzz out and form a band. That's not clumping, right? So in what?
Maybe clumping is not the right word. It's just that, let's say the J is huge.
Yeah.
So then the partons are equidistant, and
Yeah.
there is a small potential that makes sure that they are not smearing too much, that they are not smeared.
Mhm.
They're like in a trap. Each of the red points is like in a small trap.
Okay.
So it
I
cannot
see.
really get closer to its friends. But when this becomes of order this, they can easily get over this barrier. So it's
Easily.
like in the metal. So they look like it's like particles in the metal that once you get them from the orbit of the nucleus, they start being very delocalized.
But why is the gravitational force causing this?
Well, we thought for a long time that it's very important that this comes from the gravitational force compared with or competing with the electric repulsion. There is like a net attractive force that becomes important when J is of order Q squared.
Yeah.
And it lets these particles like hover in this band, as you said.
Okay.
Now, you probably are asking, why is it important that it's attractive?
No, I don't see why the gravitational effect of gravitational force would lead to a picture of particles hovering and somehow smearing out, as opposed to, collapsing and clumping and clumping together.
I have no idea, actually.
It's a semi-classical picture, right? I can see things in a semi-classical way.
No, but my point of view on this is that before you take into account this attractive small interaction, each red point is in a small trap. So I think about it like, like in a electrons stuck around the atoms in an insulator. And then you add some force, and now there is no more binding to the nucleus. And then the electrons are free to hover everywhere in the metal.
Oh, so I understand this picture. The only thing is, how is the gravitational force causing this picture? That was my question.
This small interaction that allows the red points to exit from the trap, from the small trap at which they're in, is coming from the gravitational force in the ADS picture.
An attractive force.
Attractive gravitational force between the partons, yes. It becomes strong enough to get them out.
Okay.
I don't understand why this.
I mean, you want to think of it as getting out of those traps, the small traps.
Yeah. Well, at some point, I actually thought that it's very important that it's negative. I thought that it's important for a Bose-Einstein condensate. It's important that there will be a small attractive force.
Okay.
But then condensed matter people told me that they actually observed experimentally that even with a small repulsive force, you can still get Bose-Einstein condensates. So I don't know if it's very crucial that this is negative, like that gravity wins over the electromagnetism. It does win in the O2 model, but even if it doesn't win in some other model, it doesn't mean anything at this point.
I see. Okay.
Like, I don't really know the significance of the fact that it's negative.
Okay, thank you.
I have another naive question. I mean, when you're talking about the Regge trajectory and the Regge physics, usually doesn't it mean that you have angular momentum scaling with the mass square and something like that?
Oh yes, this is what happens in a confining theory in flat space. But Regge theory in ADS leads to a slightly different formula, which is that the scaling dimension is linear in J. In flat space, we get that the mass squared is linear in J. And in ADS, we get that the scaling dimension is linear in J.
Yeah. So that's what my confusion was, because you started out with the conformal field theory, and then you said that at one point you said that the scaling dimension is related to the mass, and so that was
ADS mass.
ADS mass. Yeah. So that was what was confusing me. So I thought that you said that the conformal dimension was related to the conformal theory mass. So that's not correct, right?
Well, what people when I say the word reg, of course, it's just an analogy. So when we say that the conformal field theory has a reg trajectory, we don't mean that m squared goes like j, because there is no mass in conformal field theory.
Right.
So when people say that conformal field theories have reg trajectories, what they mean is these pictures. They mean that there is a sequence of operators for which delta behaves linearly with j.
Yeah.
And people call these trajectories, and they have daughter trajectories. So there is an analog theory of reg trajectories for conformal field theories.
Okay. Yeah, that's what I thought. Yeah.
Sorry, Zohar, just one question. Thanks for a very beautiful talk, firstly.
Yeah, of course.
The question is, I'm still trying to understand this very interesting giant vortex solution and the fact that, even though just to understand, the velocity of the boundary exceeds that of the speed of sound, is it?
Speed of sound you see, the speed of sound is defined to be the speed of the fluctuations, right?
Yeah.
So in any of those solutions, the speed of sound is 1/√2.
Correct.
And but if you expand around this new solution, the speed of sound is the speed of light.
I see, but I mean, on the outside is on both sides is the restored phase, the normal phase, is it?
Yes, 100%.
I see. So it's different from a usual vortex in a sense, which on the outside is the broken phase, is it? Here it's the restored on both sides.
Yeah, you can think about it in the following way. You can think about it on the sphere that there is a huge vortex here with a huge core and an anti-vortex in the south pole with also a huge core. So you can think about it as a huge vortex, huge anti-vortex.
I see.
They both have huge cores and they push away the superfluid. There is a very simple way to understand why the speed of sound is now the speed of light. It's because effectively the domain becomes 1 + 1 dimensional.
I see.
So the superfluid now lives in 1 + 1 dimensions rather than 2 + 1. And you remember that the formula for the speed of sound is 1/√d-1.
Yeah, I see. Nice. Okay, I understand. Okay. Thank you very much.
Thank you. Have a nice day.
You
Yeah,
too.
Zohar, can I ask a question? So the vortex to partons transition reminds me a bit of the strings to string bits transition in for strings in ADS, for example. As you tune the ADS curvature to larger and larger values, the gradient term in the string worldsheet action basically drops out, and you have a bunch of this x mu of sigma. I mean, then it's like disconnected particles. Of course, there's a gauge constraint that you still have to satisfy. That's what makes them not completely. So there is a way of understanding both the string picture and the string bits picture from the same worldsheet Lagrangian. So I was wondering whether, I mean, in spirit, these vortices are not too different from the Nielsen-Olesen.
Yeah, you're right. It might be possible to find intermediate. You see, I mean, we don't really know this full space of phases. I don't claim that we have. We just found a bunch of phases that nicely fit into a puzzle, like this picture here. They kind of parametrically look like they supersede each other, and they glue kind of nicely. But it doesn't mean that there are not other regimes. So it could very well be that within the equations of motion that we're studying, there are solutions of the sort that you described, like that where this giant vortex breaks up into clumps or breaks up into pieces or bits, and they're spinning each other, and then there is a gap like here between. So there is some red region, blue region, red region, blue region, something like bits such solutions could definitely exist, and they could be like intermediate solutions before you set into the asymptotic redshift domain.
I
Certainly such solutions could exist.
I see.
We by no means I claim that we found all the solutions. Like in the matrix in the language of, you could say that there is you could think about it as opening a cut, like another cut opens here.
Yes.
Like you could think about the density of the superfluid as somehow analogous to the density of eigenvalues or something. And so you could say that the nice thing about the giant vortex is that it opens a cut. So before the giant vortex sets in, there is a superfluid everywhere. And then suddenly a cut opens. And it's actually not yet known if the cut opens in a second order fashion, like in the Gross-Vadia model, or whether the cut opens in the first order fashion, like in the complexified Gross-Vadia model. So this is this question about the superradiant transition. Is there a superradiant transition here? Meaning, is it second order or is it first order? It's not known yet. And in addition, some cuts could open here.
I see.
So is the ADS dual a Vasiliev theory?
Yeah, here we just did O2. I don't claim that. I mean, all the ADS language that I was using is just for heuristics. I mean, this is these are just results for the O2 model.
Okay, but I mean, there's no explicit ADS dual theory, right?
No, definitely not.
Out.
No.
Okay.
I mean, a true ADS dual theory would have another large parameter n, and the discussion would have to involve what happens when Q is of order n squared, much bigger than n squared. There will be another scale.
Okay, if there are no more questions, let's thank the speaker once again.
Okay, thanks everybody.
Thanks so much, Zohar. Wonderful talk.
Great talk, Zohar.
Thanks everybody. Have a good day.
Bye.